Okay, so I only had one brave soul show up for the help session, so I decided to just do this online. So really appreciate that person. I know who they are. But this is, I gave this to y'all in class today. These were the questions from exam number 3 for the past 5 years that are, fair game for the quiz on Monday. There will be about 5 questions from chapter 4 and 5 questions from chapter 5. From chapter 4, that includes home circuits, RC circuits, and then from chapter 5, it includes magnets, the basics of magnets, what is a magnet, magnetism of the earth, and the right-hand rule as it relates to a force on a charge moving through a magnetic field, and just calculating the force on a charge moving through a magnetic field. You won't see any wires in magnetic fields or loops like we did in class today. You also won't see generators or mass spectrometers or the magnetic field, excuse me, due to a long straight wire. So just these questions, there are a few from exam 2, but mainly we're looking at exams 3. So just want to take a little time to go through some of these questions for the exam. So first of all, make sure you know how to do RC circuits. First of all, you might have something that's just asking about the time constant. Remember that tau is equal to R times C. That is the time constant, tau. And in this case, that would be R times C. That is going to be 10 seconds. But so in this case, the tau is time constant. But then sometimes I ask something else, and that is, what is the total time to charge or discharge? And that total time is equal to 10 times tau. Also here, make sure that you understand the growth and decay functions and what they look like. This is a growth function. This is a decay function. The growth function is attached to those functions that look like this, or that graph looks like that. And this graph, the decay function, looks like this. So, you can look at your equation sheet and see which ones have this e to the minus t over rc, and this one has the 1 minus e to the minus t over rc. So, as t gets big, this thing right here will approach to 0. That's why this function, has that graph where it goes down to 0. And if I have 1 minus e to the minus t over rc, then it will approach to some value that is, times 1. So it approaches some positive value. So just make sure that you know what those are. This is the voltage versus time for a charging capacitor. That's going to be C. It's going to increase with time until it reaches some maximum value. Make sure you know about household circuits, know all the different things. So we have GFCI. GFCI looks for incoming current and outgoing current. And if ever IN is bigger than I out, it will turn off. This is similar to, but different from circuit breakers. And in a circuit breaker, it's looking for the total current to exceed some maximum allowed current. So for example, this might be 15 or 20 amps is common in your household circuits. If you look on your circuit breaker, sometimes the number is printed on the switch that shows what is your maximum current allowed for that switch. So your circuit breaker turns off if that current exceeds some maximum value. And then also the ground provides an alternate path to ground. This protects against faulty devices. The GFCI is often seen in wet areas, and the circuit breaker, well, that's what it does. Well, it checks for I exceeding I max. So GFCI, that's true. Also know some other basic things of like all devices in a household circuit operate at the same voltage. You'll need to know that number, by the way. It's 120 volts. This is not true, and that's not true. So for that, this answer would be 1 and 2. So here I have these devices on a circuit, and I want to know what is the total current. Well, I know that P is equal to V times I, so then I is equal to P divided by V. So if I want to know the current for each of these, I would just take the power. For example, for the heater, 1200 watts divided by 120 volts. That 120 volts isn't given, but because it is a house, you know that everything in the house operates at 120 volts. So that would be equal to 10 amps, and this would be 5 amps, 600 divided by 120, and this would be 1 amp. 10 plus 5 plus 1 is equal to 16 amps. So that would be the total current. Um, let's look at some different ones. So that's sort of the types of questions that you'll see for, um, actually no, let's see, for the RC circuit. Let's do another RC circuit, by the way. Okay, so here's another RC circuit. Here I have an RC circuit. I want to ask, is it charging or discharging? Well, initially it has no charge, and then as it accumulates charge, I want to know what is the charge in 5 seconds. So if I look at my equation sheet, I'll see that the equation is Q equals big Q times 1 minus e to the minus t over RC. So here, Q is the Q that I want to know. That's the Q at 5 seconds. Big Q is the total charge, the maximum charge, which is going to be C times V. That's 5 times 10 or 50 microcoulombs. So this would be 50 microcoulombs times 1 minus e to the minus, well, t is going to be 5 seconds divided by RC, which is 1 times 5. So that's divided, RC is equal to 1 mega ohm times 5 microfarads. Remember the micro and the mega cancel, and that gives me a time constant of 5 seconds. So then this is my equation here. I have, I think the answer is 30 if I'm not mistaken. But if you put it in your calculator and you get 50 minus e to the minus 1, or 50 times e to the minus 1. Uh, let's see. I don't have my calculator. Oh, there it is. Let's just double check. I'm pretty sure it's 30. Your exponential is usually second natural log. Yeah, I get 31 or 30 microcoulombs. Make sure you can do that in your calculator. You're going to have to do it on Monday. Uh, Make sure that you understand just the basics of magnets and magnetic forces. The magnetic force is parallel to the magnetic field. That's true. We saw that too with electric fields. That was true. The magnetic force is always opposite the electric force. Not always true. The magnetic force can change the energy of a particle. That is true. Let's just touch on this for a second. I don't know if it'll come up, but it might. So we've talked about how magnetic forces are centripetal forces. Oh, I'm sorry, this is not true, by the way. So let me fix that. That this is a centripetal force. That is that it is a center-seeking force. So if I have a charged particle and it travels like this and then it has some force acting on it, that force is going to act to make it move into a circular path. That circular path, or because the force is not in the direction, because the force is not in the direction of the um, sorry, because the force is not in the direction of the velocity, that means that the force doesn't change the magnitude of the velocity. So, like you have your velocity in this direction and your force is in this direction, it's not going to accelerate. That is, it's not going to increase the magnitude of its velocity. Is only going to change the direction of the velocity. So we saw that with centripetal forces, and we said that centripetal forces don't change the kinetic energy of an object. That's true here too. The reason it doesn't change is because it only changes the direction, not the magnitude of the velocity. Okay, so the magnetic force can change the energy of an object? Not true. So the answer here would be, well, let's see. It should be one only. Magnetic force is parallel to the magnetic field. That's true. Magnetic force is always opposite the electric force. No, that's not always true. Magnetic force, I'm not sure why this doesn't have one only. This should just be one only. All right, electron is moving at 3 times 10 to the fifth in the positive x direction. Magnetic field of 0.8 Tesla. Hold on, let me just check on that, y'all. Okay, y'all, sorry about this. So, yeah, I don't know what I was thinking. Not really thinking. This is also not true. So, the answer to this is going to be E. And the magnetic force, so if our magnetic field is in this direction, then our magnetic force is going to be some orthogonal direction. So, for example, in that direction. By the way, while we're looking at this, while I've drawn this, what would be the direction of the velocity if this were the case? Well, I'd let my middle finger go in the direction of B, and then my force, um, is to the right. So try that with me. Let your middle finger go in the direction of B. This is hard. Middle finger go in the direction of B. Your force is to the right. That means that the velocity is going to be into the page. Okay. Be able to calculate this. So here I have a velocity equal to 3 times 10 to the fifth meters per second. The magnetic field is equal to 0.8 Tesla, and the magnetic force is what? Well, it's going to be QVB. These are all orthogonal, so I'm just going to leave off the sine theta. This is an electron, so it's 1.6 times 10 to the minus 19 times V, which is 3 times 10 to the fifth, times B, which is 0.8. And I get 3.84 times 10 to the minus 3.8 times 10 to the minus 14. Oh, that would be, no, not, it would be A rather. All right, so A is going to be the right answer, but notice it gives the direction to that force. Let's just double check that because my velocity is in the x direction. My magnetic field is in the positive z direction. That would look like this. So that's B. Now, my finger in the direction of V, my middle finger in the direction of V, that would give me a downward force. So my force would be down, except then I say, oh, this is an electron. So let's scratch that and say, no, the force is going to be up, which is what this has. While we're doing that, let's do this one, number 13. You will have several right-hand rule problems. So here I have a positively charged particle that enters a magnetic field as shown. What is the direction of the force? So index finger in the direction of V, magnetic field is into the page. That means that the force, which follows my thumb, is going to be up. That's in the positive Y direction. Here, what's the direction of the magnetic field? Magnetic field always runs north to south. Don't worry about number 11. These also, you're not going to see these on the quiz. And when you get to stuff about light, you've gone too far. All right, these are great free response, but we're not going to worry about these right now. Make sure you know about these various household circuits. There's some, you'll see similar statements, but they will be different, of course, or depending on the question. Your question will be exactly like one of these questions. The household circuit is correct, connected directly to the earth. That's true by our grounding. The transformer changes DC to AC. That's not true for household circuits. Now, there are some transformers that will change AC to DC, but for what we use it for, we use step down and step up transformers. So we talked about that in class. The transformers that we use out on our utility poles are step down transformers. They take high voltage electricity that's in the lines outside your house and step it down to a lower voltage from about 3,000 volts to about 120 volts. The circuit breaker protects the user from faulty devices. That's not true. That would be GFCI, or not even GFCI, I'm sorry, that would be your grounding is what protects you from faulty devices. GFCI2 maybe, but mainly the grounding. And then a ground fault circuit interrupt, that does turn off. So let's see, 1 and 4 are the correct answers. All right, here's another one. Oh, this is asking which ones can operate on the circuit. So you first want to find the current for each of these. That's going to be P divided by V. So this would be 10 amps. That's 1200 divided by 120. 1 amp, 5 amps, 5 amps, and 4 amps. And then ask yourself which of these do not exceed, or which of these can operate on this circuit. So the toaster, blender, and TV, that would be 10 plus 4 plus 5. That would be 19. That was not going to work. The refrigerator, blender, TV, and radio, that's 5, 9, 14, 15. Okay, that one was okay, but let's do these others. Toaster, TV, and radio. Toaster is 10, 15, and 1, that'd be 16. And then refrigerator, blender, and toaster. 5, 9, 19. All right, so the only answer possible is B. It carries 15 amps. You know, it's really the toaster, right? The toaster and any other heating device, those just carry a lot of current because they're very high powered devices. Anytime you have electricity and you're trying to create heat out of it, it takes a lot of energy. Your hair dryer, your toaster, your electric oven, your electric dryer, those are all your biggest consumers of energy in your house. Okay, here's another one. We're discharging a capacitor. When we're discharging a capacitor, that charge versus time is going to be a decay function, so it's going to look like that. So Q then is going to be big Q times e to the minus t over RC. So this looks a lot like what we did before, except, you know, the equation is a little bit different. So C times V, that's 2.5 times 12. That's 30 times e to the minus t is 10. RC is 2 times 2.5, so 10 divided by 5, so it's 30 times e to the minus 2. I get 4.1 microcoulombs. Make sure that you know how to do this. You're going to have to do it on Monday, okay? Anytime you see a wire in a magnetic field, I'm not going to do that one. Not on the quiz for Monday. But if you see one that you're not going to see, make sure you're careful that you keep going. I showed that list at the beginning. Let me show it again. Where is it? I think it's right here. Yeah, so here's that list of questions that you should be prepared to answer. For a magnet, a domain refers to, make sure you understand magnetic domains. It's not the region from where it's mined. It's not the region between the poles. It is the region in which the magnetic poles of individual atoms are aligned. And it's not the space around a magnet. So if I have a piece of material, I can imagine tiny sections within that material that have their own magnetic fields. Those are called the magnetic domain. So if you get smaller and smaller within your body, within a body of this material, eventually you will get to a point where the magnetic fields of those materials are aligned. Even if you just get down to a single atom, I mean, it has a single magnetic field, so it is aligned with itself. And we call those magnetic domains. And if I have an object that is a permanent magnet, then those magnetic domains are all pointed in the same direction like that. All right, what is the charge of this particle? So here we know the velocity is in this direction, and we know that it has a force pulling up, and then our magnetic field is into the page. So let's imagine then if I have a velocity and a magnetic field, that is a velocity like this and a magnetic field like this, what force would that give us? Well, that would give me index finger in the direction of V, magnetic field is out of the page, so that would give me a force that would be like this. So this particle would tend to follow that path. And since it doesn't, then I know that the charge of that particle is negative. Okay. All right, here's some more. GFCI, that's correct. Make sure you're very clear on the difference between GFCI and circuit breaker, okay? Devices operate all at the same voltage, that's true, 120 volts. As you add more devices to a household circuit, the current increases. True, true. So as I add more resistors in parallel, the total current increases. And the current to a device in a household circuit would decrease if other devices are removed. That's not true. That's why household circuits are not laid out in series, because if they were laid out in series, when I add devices, the overall current would decrease, and that would be bad, or your voltages would decrease. So here our answers are 1, 2, and 3. Here's a similar question here. I have, remember, I is equal to P over V. So I have, then this is 240 over 120, or 20 amps. This is 1 amp, and this is 0.5 amps, and this is 4 amps. So I have 21.5 amps. I add 4 amps to that to give me 24.5 amps. So somewhere between 21.5 and 24.5, I have the thing turning off. Excuse me, 25.5. So that's not that one, or that one. The A then is the right answer. All right, I think we're going to wrap up here. So make sure you practice all those questions. If I didn't work the question here, I've done many of them, but if I didn't work them here, make sure you go back and practice them on the old exams. The videos are really useful for you to practice and use as a resource, but I find that you're really not going to get it unless you are trying it all on your own, struggling through the questions all on your own. And then if you get them wrong, then you go back and watch the video and see where you got it wrong. So make sure that you're practicing them. Uh, you know, there aren't as many topics on this quiz, and the topics aren't as complex as in past quizzes when we were doing circuits and the like. But, it is going to be a difficult quiz. So make sure that you put in appropriate time. I want everybody to make 100%. Okay, y'all have a great weekend. Bye.